Before we look at some examples, let's talk about in general how we should be applying Gauss's law. So as we stated in the last video, to easily apply this, we need to have a symmetric charge distribution. If we have a non-symmetric charge distribution, we need to use Coulomb's law. So what we're going to do in applying Gauss's law is we're going to construct a mathematical surface called a Gaussian surface. So of course this isn't a physical structure, it's just some mathematical model that we're utilizing. And so we're making this Gaussian surface such that our electric flux density D is normal or tangential to the Gaussian surface at every point, and such that our D is constant on the surface. And so let's take a look at what the D being normal or tangential to the surface means for us. So if we have that our electric flux density D is normal, then in our integral form of Gauss's law, we're going to have the surface integral of D dot ds. Well, that's just going to become the magnitudes, so D times ds. If the D is tangential to the surface, that same dot product, D dot ds, is just going to be 0 because our D and ds are going to be perpendicular to one another. So with that in mind, let's look at a simple example of a point charge. So let's say we have some point charge Q which has at the origin, and we want to know the electric flux density at some point P. And so I can just put some arbitrary point P. Of course, we can put this wherever we want. So our approach with using Gauss's law is we say, all right, I want to define a Gaussian surface such that our D is going to be constant everywhere. So if we want D constant on our surface, we can sort of either intuitively know for a point charge that the only real dependence on the electric field or our electric flux density is going to be the radial distance from that point charge, or we could think back to our analysis we had done previously with Coulomb's law. So basically, we're going to have D constant on a Gaussian surface that's a sphere. So what this means is we're going to have some sphere, and so our sphere should intersect this point P. So let me move my Q around so we can, well, let me just get rid of that and redraw it over here. So we've got some Q, and then let's say we draw a Gaussian sphere, and so I'm really just going to try to do a circle, and so you kind of have to use your imagination to fill in there. But that green circle represents a Gaussian sphere, and the distance from our Q, which is at our origin, to our point P and any other point on the surface of that sphere is going to be r. So we can say sphere with radius r. All right, so now from Gauss's law, we're saying that our total charge Q should be equal to the surface integral of S, and remember it has to be a closed surface, of D dot ds. And so we've intentionally defined this such that at that point P, we're going to have our electric flux density is going to be purely normal to the surface. So because of that, we're going to reduce this integral. So our dot product is going to become the integral over the closed surface of dr times ds. And so dr would be our r component. And of course, in this case, we already kind of know that our D is only going to have an R component. And because we said that this D is going to be constant on the surface, that means with respect to changes in ds, this dr is constant. So we can go ahead and pull that out of the integral. So we get dr times the integral over the closed surface ds. And so now we're integrating over a ds. So we have Q equals dr, and so for this ds we have phi and theta varying. So we have phi is going from 0 to 2 pi, and theta is going from 0 to pi based on the limits for our ranges, and then our ds for this sphere is going to be r squared sine theta d theta d phi. And so that is our r direction ds from our spherical coordinates. So we evaluate this, and we get dr times 4 pi r squared. Okay, so now remember though, this is equal to our charge enclosed, which is equal to only our point charge. So we're assuming only the point charge is in that green sphere. So of course we can rearrange, and we can then say our d, because we know it only has the r component, is equal to, in the numerator we have q, and we divide that by 4 pi r squared, and that's going to be in the r direction. And that's our result. And so we can compare this to what we had for our electric field on page 4-5 in the notes, and we'll see the only difference for our electric field is that we had an epsilon naught term here in the denominator. And so we can see that this is, I think, a fair bit easier than using our Coulomb's law to find our electric field, and we'll see that's actually more so true with some more complicated configurations.